So in this video, we will do an example of implicit differentiation, and we will find the slope at a point on on a graph. And while we're at it, we might as well find the tangent line too. We'll go ahead and do that as well. So here's my here's the equation: y equals x over y. And you can ask, what does that look like? Well, you can throw that into a graphing calculator like Desmos.com will do that. Another option is to just multiply. Let me change colors here. If I multiply by y on both sides, you get y squared equals x. Looks like a 4. It's just a bad y. It's a y. So y squared equals x. The graph of that looks like the following. You might recognize that, it looks like a parabola. Like it's kind of like x squared equals y, sort of. It looks like the same format, but the x and y coordinates are switched. So whereas normally a parabola would look like that, right? Well, like that. This one is going to look like this. So this does not represent a function, okay? So if I try to get y by itself, that's not really going to work. We can do that, but we're not going to get a function that way. We're going to get something like y equals plus or minus the square root of x, and then trying to find the derivative of that is its own problem. So I can either go back to the original equation to find my derivative, but then I'll be stuck with the quotient rule. I'd like to avoid it if I can. I want to do the easiest derivative process as possible, easiest thing I can come up with. So I'm going to find the derivative of this guy instead. So that it's a little bit easier than previous videos. If I hadn't done that rearrangement, well, then that would be more complicated. But I want to avoid that if I can. So I'm going to find the derivative of this equation by applying d dx to both sides. Okay, so d dx of y squared equals d dx of x. So on the left, I'm going to have to apply the chain rule because I'm going to find the derivative of the outside function and then multiply by the derivative of the inside function. So the outside function is the squaring function, some expression squared. So that's the derivative. Use the power rule, 2 times something, right? In other words, the derivative of x squared is 2x. So that's what happens to the exponent. It just moves in front. The new exponent is a 1. I need to multiply by the derivative of the inside function. Well, the inside function is y, so this is dy dx, and that equals, and the derivative of x with respect to x is just 1, so we get 1. And I'm going to put this inside function back in. So I end up with 2y times dy dx equals 1, and then I can divide by 2y on both sides and get dy over dx equals 1 over 2y. Okay, so that is the derivative of that equation, and I can use it to find the slope at the ordered pair 1, 1. That was the original statement of the problem. So the slope there, slope at ordered pair 1, 1, well, this is going to be dy dx evaluated at the ordered pair 1, 1. Basically, you'll plug in 1 for x and 1 for y in the derivative formula. Now, in this case, there's no x in the derivative formula, but oftentimes there will be. It just depends. So this is going to be 1 over 2 times 1, or in other words, 1/2. Okay? So that's the slope at basically this point right here. That's the ordered pair 1, 1, roughly. Of course, I'm drawing this by hand, so it's not that well done, but that's roughly where it is. And it kind of looks like the slope is 1/2, roughly. Now, if I want the line there, the tangent line there, then I can do this. I know the ordered pair, I know the slope. I can use y equals m, better m times x minus x1 minus y1. So m, that's the 1/2, that's the slope that we found, times x minus, well, x1, that is the x coordinate in the ordered pair that we're talking about. So 1, and then minus y1, which is again 1, just like in this case, x and y are both 1. So there is an equation for that line. I can clean that up a little bit. I can distribute 1/2 x minus 1/2 minus, oh, I'm sorry, I have a mistake here. That's not supposed to be minus y1, it's plus y1, my mistake. Plus 1. So we get y equals 1/2 x plus 1/2. And if you graph this alongside uh, this equation, you'll find that that is indeed the tangent line. You can go to an online calculator and that'll do that for you. But maybe we can do that right here and switch over to Desmos. And I can go here and say, well, I want to do, say, y squared equals x, right, which is the parabola. And then I can do y equals, a little hard to type here, 1/2 x plus 1/2. And you can see that that is the tangent line at the point 1, 1.